the Gauss elimination method. We have discussed about the redecomposition method. We have discussed about the part of redecomposition, Cholesky factorization. We have discussed about the Thomas approval part. So, other thing is actually remaining that something called matrix inversion. Matrix inversion. What we have to find out A inverse. How to find out A inverse? By the method what actually we have discussed. Any idea? How to find not Gauss Jordan method, very expensive method. How to find out A inverse to the matrix? That is not the numerical technique, analytical technique. The big matrix is there. If you do actual determinant, that's it. It's very expensive. I told last class also. Right? If you do by when more than 10 by 10, you start finding determinant. And 10 factorial terms with the right determinant, right? So if you're finding A inverse, will be very expensive if you do analytical way. So how do you do numerical way? A inverse equals to I then. Gauss Jordan method is not useful. That also I discussed. It's very expensive. How to find A inverse numerically? Okay, I'll give you the hints. How to find A inverse using redecomposition method. Using a redecomposition method. How to find A inverse using redecomposition method? Any idea? Any guess? Not one row of A inverse. Not you are saying like this is not row, it is column. That is the way you say, you think something and tell something else. Okay? You are saying like this means row only. Okay? So it is A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANn. This is A matrix, right? A inverse matrix we don't know. We put A11 prime, A12 prime, A1n prime, A21 prime, A22 prime, A2n prime, AN1 prime, AN2 prime, ANn prime equals to 1 0 0 1 0 0 1. Okay, this is your A matrix. This is A inverse. This is I matrix. What actually happens? You take A matrix, take this row. We have A11 prime, A21 prime, and AN1 prime. You get what? 1 0 0, right? Next, you get A matrix. We have second column A12 prime, A22 prime, AN2 prime. You get 0 1 0. Like that will go. So now, why I am saying redecomposition method? If you look at in this system, we are having a system where we have Ax equals to B prime. On the right hand side is changing, left hand side is fixed, which is A. This A matrix is like Ax equals to B. This X is changing because of B prime is changing. Similarly, A is fixed here, X is changing. So if you take one column, multiply, you get this one, right? So now in this case, what happens? Once you find L matrix and U matrix, these have been stored, and it is easy to solve by redecomposition method. Gauss elimination method means every time you have equivalent. So for this kind of system where matrix is same, but only B matrix in B vector is changing, in that case redecomposition is very powerful, and that powerful technique is useful to find the A inverse. Vanda is clear? Okay? So this is the way one can actually find the A inverse. Okay. Next I would like to discuss something on partial pivoting. Next I am going to discuss on partial pivoting. What is partial pivoting? Any idea? For example, we are actually having a system 2, 3, 5, 3.7, sorry, 0, this type of system. So when you look at this type of system, always look at the entries. You can see this is more the magnitude of this. Sometimes you can have minus 3.7. You don't look at the minus sign. You look at the magnitude. If the magnitude is the maximum, so what you do, you interchange this. So it is minus 3.7 here, 2 here, 5 here. So what will actually happen? This entire equation has to be replaced by the first equation. So what is this? Equation 1, 2, 3. So what we will do? Partial pivoting means you will see the entries. This is maximum. So our rule is that this has to be maximum. Okay? And sometimes what actually happens, you may have 0 here. And in that case, how will you do Gauss elimination? Gauss elimination will fail, right? If it is 0. So what actually happens then in that case, you look at the maximum entry, replace it. So if you have 0 entry here, if you want to do Gauss elimination will fail. Because once you start dividing by A11 is 0 and every entry is actually having a problem. So partial pivoting is actually useful for this type of system. So whatever we do that, the partial pivoting, if this type of situation will not occur, then we are okay. But if this type of situation occurs, then you need to do partial pivoting. Partial pivoting means interchange the rows or interchange the equations. As you see, interchange the equations. If equation 1, and then what actually may happen that after the first iteration, you may have the diagonal term is 0. The diagonal term is 0 when which is being scaled. That particular equation again it has to be interchanged. For example, after say iteration you are getting 3, 2, 7, 0, 0, 5 and 0, 2, 3. This type of situation again a problem. Interchange start to second. So this is called as partial pivoting. This is known as partial pivoting. This is known as partial pivoting. Okay. There is something called complete pivoting. I will not encourage because complete pivoting means you have interchange column. If interchange column, entire thing is jumbled up, and that is not expected because if you interchange rows, interchanging rows means interchanging equation. That's okay. Interchanging rows means interchanging equation. Interchanging rows means interchanging rows means interchanging equations. Or interchanging column means I have shown you that column means something dangerous which we will not do. Pardon? What is that? I am not able to hear what you are saying. I am not interchanging anything here. Of course interchange. I am not doing interchanging rows means it is like entire row. How? What are you saying? I thought it is so trivial. If you are asking me this kind of question, I don't know. Okay, I am going to 7th standard problem. I am doing partial pivoting in a 7th standard problem. Is that okay? That is the way we want. How to write 1, 2, 0, 1. x1, x2, 3. But this is not the case. What actually could be the case, equation is given like this: x1 plus x2, 2x equal to, or could be x1 equals to 1. This case will be what? 0, 1, 0, or okay, I put x2 equals to 0, 1, 1, 2, x1, x2 equals to 1. I cannot solve like this by Gauss formulation. So what I will do? I will replace the equation number. If I replace the equation number, D also has to be replaced, no? This question actually I don't know. If you go to this level and ask me the question, I don't know where I am, where are you? No idea. Like this only, right? The point is what actually exam what person did, he replaced these two also. That's what he is asking. If you replace mine, you can do whatever you want. I will do whatever I want. Okay, there is no point to teach you anything. Some of my friends, what they did x2 and x1. Then I gave 0 mark. Then person came and told me, sir, you are wrong, I am correct, because x2 was also replaced. Okay. Then I said, I don't know who is correct or wrong, you have learned. You can also do the same thing, you can replace everything. That's what she was asking, replace everything. You see whatever you are getting, I see whatever I am getting. Finally, I have to agree with whatever I want to get, right? You can do whatever you want, no problems, it's a democratic country. I also want whatever I want to get. Finally, I didn't win because I have to finally decide the grades and all. Okay? Panda clear? Madam, everything clear? That's what you are asking, no? That's what I think. When you are in doubt, you go to 7th level mathematics. Right? Class 7th standard mathematics is enough because my math course is very easy. Sometimes you need 7th standard mathematics, sometimes you need 12th standard mathematics. 7th and 12th, if you combine them, that's the mathematical methods of chemical engineering. Okay, huh? Okay, good. So, partial pivoting is also done. Okay, now situation is, when you are doing this type of 7th standard mathematics, what is your problem? Your matrix is 0, 1, or sorry, I will just write my usual 1, 0, 1, right? By doing some numerical techniques in computer, what actually happens? You do 1, 2, 0 and 1.005. This is numerical error. If this type of numerical error occurs, then what actually happens? It will affect the solution. Okay? So when you do analytical solution, okay. When you do numerical solution, there is something called round off error. I will discuss, if you have this type of system, we will show this will pose something called ill-conditioned matrix. So now we will be discussing something called well-conditioned matrix and ill-conditioned matrix. So what I am saying that you are solving Ax equals to B. By doing round off, your matrix is approximated by A plus delta A. Your B vector is approximated by B plus delta B. Why? Because I am saying that instead of 3 and 1, we can have 3.001 and 1.001. So this is the perturbation vector, B plus delta B. And perturbation matrix is A plus delta A. So that will give the perturbation part of solution. Slight perturbation, not a big part. Big perturbation means big error. A small perturbation means, will the error be small? That is my question. Will the error be small? If I perturb slightly, will the error be small? We don't know. How to quantify the error? Quantify the error means the length of this vector delta x. What I am saying that this is your exact solution, okay? This is your approximate solution, and this is the error. So x bar plus error equals to approximate solution, right? How to quantify the error? The quantification of error is x prime minus x, and you will take the norm of this Norm is the length of the. But if you look at, if you want to talk about norm of delta x, it involves a, delta a, b, delta b, so many things. So it is the right time to if you want to quantify the norm of this guy, delta x bar, which is the error, x bar is the actual solution, delta x bar is the error, because of the perturbation of the matrix in A plus A, which is now termed as A plus delta A, and the perturbation in the vector B plus delta B. So you got the error delta x. Right? To quantify delta x is not very straightforward. You need to have the concept of the norm of matrix. So now we will actually have the, so we have the property of the vector space, right? Norm of the vector space. What are the properties? Let me look at the properties of the norms of the vector space. We have already done it long back. So we will actually have a recap of the vector space. Then we will go for the norm of the matrix also. Okay. So norm of a vector space. What are the properties? Can you tell me? You have with your notes, or you don't have notes? You don't carry the notes. Okay. So if B is the vector, B belongs to capital B. Long back we did, maybe some few decades back. Okay, which is greater than 0 for all B belongs to capital B. Okay. Equality sign holds if B equals to 0. This is now vector. Number 2 is norm of alpha B equals to norm of or mod of alpha into norm of B. For alphas belongs to what? Scalar. Numeric field. Alpha belongs to numeric field. Okay? And for all alpha belongs to numeric field and B belongs to vector space. Number 3, if there are two vectors B bar and W bar, we have derived it already plus W. Where we can say for all B bar, W bar belongs to capital. This we have learned already. We have looked also all the properties. This for the vector space. So now, vector and matrix, where is the commonality? Vector has magnitude and direction. How many directions? How many direction vector has? 1, 2, 3, 4, how many? How many directions the vector has? Huh? Only one direction, right? 8 directions, huh? Okay, Sir is saying something. Let me think about 8 directions. This is a vector. No. You are saying 8 directions. This is the point. This is the way we have learned it. 8 directions, it has 3 directions, huh? It has 2 directions. No, what I think Sir is meaning that, I will tell you. Sir thinks in different dimension. And my dimension is much lower. So he is a tensor of a vector. Small vector. Because I am only unidirectional is multi-directional. I will come to tensor. What Sir is thinking that if you go this way and this way, you can reach here. Okay. So it has got 2 directions. Then Sir also thinking other way. Sir is thinking if you go to this direction, then come to this direction, and come to this direction, 3 directions, 3. That is the way you must be thinking. That's what, so if you talk about this vector, it has got 3 directions, right? Talk about this vector, it has 2 directions, right? So that means it is having 2 directions, having 3 directions. Does that give meaning? You only told vector has n directions. Just now you told it, all people are witness, right? It has been copied in iPad also. Right? Now how many directions? I don't know. 1 direction. Now he is admitting 1 direction. How many directions matrix has? This guy also matrix. So this is vector, right? This is also vector. And this matrix and vector multiplication is vector. So this matrix will be having, it is not a scalar quantity. Okay. How many directions matrix has? How How many directions matrix has? Where do you learn first matrix? Which course in chemical engineering? We have seen matrix first. A chemical engineering course has introduced matrix first. Which course? Huh? Process calculation. Huh? Which process calculation course you have learned the tensor? I have not seen tensor in process calculation. I have seen vectors. Chemical species you can talk about, no problem. Which course? Process control, which tell me no? You don't tell me the course, you tell me example. Multiple not with tensor? Yeah, that's what. Matrix, I'm just taking this outcome. Because we are actually talking in terms of the applications in chemical engineering. Fluid mechanics, answer is very good. Which quantity? Stress. Why stress has got two quantity, two directions?
Because force acts in one direction, momentum changes.
Not momentum, force by area. This is a wrong definition actually. The stress is force by area, right? It is wrong definition. All physics books are wrong. All books are there. I am not agreeing, I am not denying that books are not writing. Books are writing because you understand better this one. It says what? It says you are getting some quantity which is the ratio of two vectors. Okay? And books are not writing stress is tensor. Books are writing stress is scalar quantity. And I asked one person, he said, words are very simple. You are dividing vector and vector get cancelled. You get scalar. Some person told me, some physicist, I won't tell the name. He said, sir, vector and vector will get cancelled, you get stress is scalar quantity. In fact, in your book and all, you have seen stress, right? No, you are too early for the next class. Okay? So, up. So, what actually happens is stress. So, basically, what actually happens here, stress is actually defined by the tensor, T double bond. Okay? And what is this force? This force is actually you take the dot product. So, the rule is that this is the normal direction, and this direction is actually nothing but direction along the area, it's called area vector. So, you are taking dot product with normal direction. So, the rule is second order tensor, it has got two directions. This is one direction. So, 2 plus 1, 3. And if a dot product comes, minus 2 will get reduced by 2 order. That's why you get force. So this is the exact definition of the stress. The point is, why these books are writing like this? Because kids will not understand this kind of concept. Kids will not understand this kind of concept. So what actually happens is T. So when I write F, we write A phi di. Right? What is di? Directions. If I write I equals to 1, 2, 3, Ramanjan will say the 3 directions. It's not that. They are components. Not 3 directions. This Tij, we write Tij, Ei, Ej. 2 summations. Right? Okay? I is 1, 2, 3, J equals to 1, 2, 3. So T represents 3 by 3 matrix. Right? T represents because we have T11, T12, T13, T21, T22, T23, T31, T32, T33. So we call this as second order tensor. And we call this as first order tensor. That means number of order in a tensor is nothing but number of direction. Okay? So vector is basically nothing but first order tensor. A tensor by default is second order tensor, and its scalar quantity is the order of 0. See, we have got it. That means 10% of the transport course of the next semester has been covered here. The next semester transport course will be started from here. So, in transport process, transport phenomena and all, we never talk about the scalar quantity. So, scalar is, in fact, in fluid mechanics, is there any quantity scalar? Sure. Pressure is vector. Huh? Pressure is vector or scalar? Pressure, how do you measure pressure? Huh? What do you measure pressure? What is the unit of pressure? measure. Definition of pressure. Force by area, right? That means what? Pressure should be called as what? Based on what we discussed. Yes, somebody said tensor, correct only. Again, pressure has been defined wrongly in the book. Something Amit is giving high fund stuff. You know, let us listen what Amit is saying.
It's a diagonal matrix if you are putting pressure, so it says tau xx, tau y, tau z.
It is not correctly what you are saying. It is an isotropic one. Isotropic tensor. This is isotropic tensor. And diagonal term all are same. Not tau xx, tau y, tau z. So, in fact, I don't know, discuss all those things will be covered in the next semester transport phenomena. This total stress tensor, you can be decomposing the pressure tensor and the shear stress tensor. And pressure is nothing but a tensor. So pressure is a tensor, is not a scalar quantity. That will be discussed because which will be the part of the total stress tensor. Similarly, what is viscosity? Is a scalar quantity. What is the order of tensor of viscosity? Is it a vector? Of course not, right? Viscosity is not a scalar. Then what is viscosity then? What is viscosity then? Ramanjan, any idea viscosity? What do you think? Viscosity will be what? Scalar? Huh? And now, yeah, we just use a scalar quantity, correct only. What is viscosity? Is a fourth order tensor, not even second order. So viscosity, fourth order tensor. So all those things will be covered. I don't know how to discuss here because you'll be really confused. It will be discussed. Sir will be coming next semester, transport phenomena, and we will discuss all those things. Okay. So we will see that, and from the fourth order tensor of viscosity, it is possible to prove the Newton's law of viscosity. You know that all those kind of things will come. Coming back to that, since these are all tensors, this tensor we have found the norm. So this tensor also can be expressed, can be having norm also. First order tensor has norm. Second order tensor also have norm. But there are some differences. Let's discuss. So let's look at the matrix norm. Let's look at the matrix norm. Number one, norm of A greater than equal to 0 for all matrix A. Then A belongs to a tensor space, not the vector space. A belongs to a tensor space. Number two, we have just compared the properties. Norm of alpha A equals to mod of alpha into norm of A. So far, everything is matching. This tensor and this tensor both are having same norm. That at least norm means what? This tensor's length. This matrix's length. Okay, what actually happens? Stress. When we talk about the stress, what actually happens? Due to the direction of the force, the direction of the force I'm applying, and the direction of the normal. So, if I want to find out the stress has got two directions. And of course, any quantity has the magnitude, right? Doesn't matter. Vector has magnitude. Okay? Vector has what? Vector has, this is the magnitude we talk about. Here it is very difficult because there are two directions. So in that case, it is possible to have magnitude. So any quantity can have magnitude, and that magnitude is termed as norm. So matrix also has norm. Number 3, norm of A plus B will be less than equals to norm of A plus norm of B. So far everything is okay. But things are not as simple as we think. So now we have to have compatibility. That means when we have the both matrix and vector in the system, that means one is second order tensor, another is first order tensor. When operating them together, there should be something called compatibility. So a matrix norm is compatible with vector norm if norm of A x less than equal to norm of A norm of x. That means when we define a norm in matrix, we need to verify these three properties. Not only that, we need to verify this property also. And there is another property called submultiplicative property. Submultiplicative property. What is that? There are two matrices A, B. Norm of A, B should be equals to norm of A, norm of B. That means when you define a norm of a matrix, we have seen the definition of the norm on the vector space. How do you define the norm? Summation of bi square whole to the power. That is the sum norm. Sometimes we say max infinity value. Sometimes we can say maximum of this. There are many ways we can define the norm of the vector space. Similarly, in many ways we can define the matrix norm. The definition could be anything, whatever you feel comfortable. But these three properties, along with this compatibility test and the submultiplicative test, have to be defined. I will give you an example. So, how to define the vector? This vector norm. Norm of vector we defined as summation di square whole to the power. This is the two norm we say. Sometimes we define infinity norm, which is max of v1 to vn, which is maximum we can take the norm, which is called as infinity norm. Similarly, for a matrix, we can also define something like summation aij square whole to the power half. Sum over I, sum over j. You can define this kind of matrix norm. This type of norm is called as Frobenius norm. F-R-O-B-E-N-I-U-S. Frobenius norm. Norm of A is like exactly like the same thing. You are taking all the entries of aij, take the square, sum it and take it up. Frobenius norm. Sometimes we can also have norm of max of mod aij like this. You just see the values. For example, 1, 2, minus 5, 3, 7, minus 10, 4, 15, minus 15, 0. What is the infinity norm? 15 only. Like that. Sometimes we can have norm which is the eigenvalue, lambda max. That also can be measured as a norm. Whatever we define the norm, it should support all those properties. Otherwise, problem. I will just give one simple matrix and show you whatever norm you define may not be correct.
Sir, attendance. Attendance sheet.
Attendance sheet.
When we are taking the norm of a matrix, there's two directions. Which direction are we looking at? And we find the information.
Both directions. What we have done here? One direction only. There are two directions, two summations. What does it mean? If I want to find the norm of this by Frobenius, how to write it? Summation 1 square, 2 square, minus 5 square, 3 square, 7 square, minus 10 square, 4 square, minus 15 square, 0 square. That's it. Why you are complicated like very simple? Things are not that difficult. Numerical is very simple. A school level kid can do better than me actually. Okay.
Sure.
So now I give you a matrix. 1, 1, 1, 1. Simple matrix. All 1. 2 by 2. I am asking you, I want to have this definition. Norm of equals to max of mod aij, which is equals to 1. Right? be infinity? That is also 1, no? 1 only. What is AB matrix? Can you get me answer? If you multiply, what will happen? All 2. So Amit is very good in matrix multiplication. Okay, maybe I should give 3 by 3 matrix multiplication in the next semester. At least Amit can do it. Norm AB infinity equals to 2. Now tell me, is this property now satisfied? This coming 2 is less than 1. That means this property, this definition of norm is not a valid definition of norm because it does not satisfy the submultiplicative property. See how nicely I gave an example. Simple matrix I have taken and I found the definition of norm is not all the time valid, and this is one of the classic examples. Okay. And as I said, sometimes what actually happens, best norm is the eigenvalue. Okay, so eigenvalue sometimes decides good norm, good definition of norm. So let's look at the same matrix A. 1, 1, 1. This is the computational numerical error. We are doing numerical techniques, so we will do a lot of error. Numerical means all kind of approximation only. What is the eigenvalue of this problem? Maximum eigenvalue. And what is A inverse? Who can tell me the A inverse? This you can do adjoint of A divided by determinant of A. That you can do. Remember the determinant of A is non-zero. If I put 1, it will be 0. Since it is not 1, it is non-zero, right? How much is A inverse then? This one is 1. Sure. What is determinant? How much is determinant? That means what? 1 by 0005 means how much is coming in calculator? 1 by 0005. You have, I think you don't have calculator. You don't have calculator. Shall I buy you one more calculator? 2000. Yes, Amit knows very good calculation. Excellent calculation he knows. 2000. Very correct. 2000. So Amit is very good in numerical analysis. 2001. Yes. Who said 2001? Because you are also very good in numerical calculations. Amazing. You are expert. You have got 2 experts in numerical analysis. Next term. Minus 2000. Yes, you are very correct. Then minus then okay. So now what is the eigenvalue of this problem? First one. What is the eigenvalue of this problem? You calculate, we will come back to this problem. Yes. What is the maximum lambda max here? Lambda max is 2 you are getting. Are you sure? How much is lambda max here? Our numerical experts are there. Let them comment on this lambda max. Amit, lambda max you calculate 2 by 2. Numerical experts. What are the lambda? 2 lambda values will be there, right? For the first matrix. What are the 2 lambda values? How much? See, how much you got lambda max? You tell me that lambda minimum. will be what? Minus 2.5 into minus 4. So I am saying that matrix A norm is lambda max. Right? Now the question is, if lambda is the norm of the matrix A, what will be the norm of A inverse in terms of lambda? Can you prove it? Ax equals to lambda x. X is the eigenvector. What actually happens? Norm of Ax equals to norm of lambda x. Am I correct? So far everything is okay. I am just taking note. Then what actually happens? Compatibility property will be what? Am I correct? Then what actually happens? Ax is what? Lambda x, right? This means lambda x, right? It says also, if you actually in that case you can also write like this because value is scalar quantity. Okay? So it says that if you now you can actually take away this x is length actually the factor. So it says that maximum value of norm is always greater than lambda. That means lambda cannot exceed the norm. It's a very beautiful proof. You can see that. It says that. That means it's a very good measurement of norm. Lambda is a very good measurement of norm. Right? What it says that norm of A, the minimum of norm of A is lambda. So lambda can be a measurement or it should be equal to lambda. So mod of lambda can be measurement of A. So what is the A inverse norm? What is the A inverse norm? So you can write Ax equals to lambda x. So what will actually happen? A inverse x equals to Ax equal to lambda x means what? A inverse x equals to Ax equal to lambda x. A inverse x equals to what is that? Ax equals to lambda x. I don't know what is your batch. X equals to lambda A inverse x. Agree or not? Then you write 1 by lambda A inverse x. Okay? So that means if x is the eigenvector and lambda is the eigenvalue, A inverse eigenvector is same, but eigenvalue is 1 by lambda. So what is the norm of A inverse then? If lambda max is the norm of A, what is the norm of A inverse? What is that? Lambda minimum. Because 1 by lambda minimum will be lambda max for A inverse. Right? You keep that in mind, we will come back. So these two are very important. Lambda max is 2. We agree with that? Lambda minimum mod is 2.5 10 to the power minus 4. I will take another 5 minutes to now show what I am going to show here. So we have perturbation A plus delta A, x plus delta x equals to b plus delta b. Now we got ax plus a delta x plus delta ax plus delta a delta x plus b plus delta. Delta is small, this is neglected. Both are very small quantities and that to multiply. So we have ax equals to b, a delta x plus delta ax equals to b plus delta b. B and b gets cancelled. We get delta x equals to a inverse delta b minus delta a x. Do you agree with me or not? Yes or no? Norm of delta x equals to norm of A inverse inverse delta B delta A x bar whole, and I will apply here compatibility property. If I apply compatibility property, which will be A inverse delta B minus delta A x next step. Then what actually happened with these two are vectors, and we have seen the third property of the vector space, vector norm, which is norm of u plus norm of b is less than or equal to norm of u plus norm of b. So delta x norm is less than or equals to A inverse into delta b. We can also put plus, still the things will hold, which will be delta A x, which is again I will use compatibility property again. Delta is a matrix, so still the less than or equal to sign will hold, and delta A x. So now we can write delta x by norm of x less than or equals to A inverse into delta B by norm of x plus delta A. And what actually happens? Norm of delta x by norm of x equals to A inverse. I take A common also, norm of A common, which will be delta B norm by norm of A, norm of x plus norm of delta A by norm of A. Ax equals to, you can write b. Still this is valid because Ax norm of b is the less than norm of A and norm of x. So you can see that this is defined as k of A, which is called as condition number, which is called as condition number. So this norm of A inverse and norm of A, right? So what we can write, lambda max by lambda min. Am I correct? Yes or no? Lambda max by lambda min. So now this is the error, proportional error, right? This is called proportional error. This is the error in the solution. This is the actual solution. Length of the solution. If you look at now for this type of matrix, simple 2 by 2 matrix, lambda max by lambda mean is 10 to the power 4. Am I correct? So if you do this kind of round of error, you will get this kind of yield condition system. And what actually happens for the yield condition system, sometimes it will be very difficult to have the converse solution. So matrix will become yield condition. So K is the condition. When K is equals to 1, matrix is well condition, you will get very fast convergence. If the matrix is yield condition, you won't get the quick convergence. So you can see that a simple matrix will lead to the complex form of the error. Thanks for your attention. We'll discuss from here on.